Okay, so assignment 2. We'll start from section 5, discussion of related work. And we'll start from question 2. How has prior work approached the same or similar tasks? So, as the online fashion industry grew, there was more need for personalized fit prediction, meaning predicting whether a piece of clothes fits the user or not. So here is a paper from 2017 recommending product sizes to customers. This paper argues that fit prediction is a physical problem, so there's not much preference involved, meaning that a user's latent factor U represents the user's physical metrics, for example, body part sizes, etc. And item's latent factor V represents the item's physical metrics. And thus, in collaborative filtering, instead of multiplying the latent factors, right, U times V, we should rather subtract them, U minus V. And if U minus V is 0, the user size equals the item size, and that's a perfect fit. And then this paper is the dataset provider from 2018, decomposing fit semantics for product size, recommendation, and metric spaces. So this paper argues that fit prediction is not purely physical. There are personal preferences involved, and so the latent factors U and V may include more than just the physical sizes, right? And thus, just like other collaborative filtering recommenders, we should just do U times V and see if the user and item match or not. Okay, so now back to question 1. How has this dataset or similar datasets been used before? So Misra et al., the dataset providers, they used ROC AUC instead of accuracy as the evaluation metric for their models, and this is due to class imbalance. So over 70% of the rows are fit. So even a model that predicts fit for all inputs can achieve a high accuracy, which is why we're not using accuracy. We're using ROCA UC. And here you can see that they used 5 models. We are going to look at the second row because Run the Runway is the dataset we use. Is the dataset I use for assignment 2. So this is their baseline model. So here they were testing U minus V on a logistic regression model, which achieved a 0.61 AUC. This one, they were testing, again, U minus V on logistic regression, but this time their embeddings were k-dimensional instead of one-dimensional, as they used for the baseline. So for this model, it achieved a 0.676 AUC. Next model, they were testing U times V on a logistic regression model, which achieved 0.672. And then these two models, they were using what they call metric learning, which is basically like a mathematical model they implemented using large margin nearest neighbor. And then again, they were testing U minus V on this model, and they got 0.681. Last one, they were testing their metric learning on U times V, so they got 0.719. As you can see, the LF which refers to U times V, did better than the U minus V models. And so their conclusion is that, right, U times V is better. And moving on to the third question, how do your results match or differ from what has been reported in related work? So my result actually disagrees with Mishra et al. So at least for this data set, run the runway data set, it seems like the physical interpretation of latent factors works better. So U minus V works better. Both logistic regression and neural network. So I implemented both, and they both confirm that the difference function does better than the multiplication function, at least for this data set. So now section 1, identify the predictive task you'll study. Question 1, describe how you'll evaluate your model at this predictive task. So the task is to predict small or fit or large using explicit and implicit user/item features. Explicit means features that's already present in the dataset. Implicit means the user and item embeddings. So we will use ROC-AUC to evaluate the models, and this ranges from 0 to 1. And how you get it is basically you calculate the true positive rate slash false positive rate at all possible decision thresholds, and then you graph it and calculate the area under the curve. So the higher is better. 1 means perfect model, and then 0.5 means random guesses. So if your AUC is less than 0.5, that means your model is totally useless. And so we use ROC-AUC for classification tasks when there is a class imbalance, in which case you want to use accuracy. And specifically for this task, we will use one versus rest ROC-AUC because we have multiple classes, and then we need to predict one of them. So that's a multi-class soft max task. Basically, one versus rest asks multiple binary questions: small versus not small, fit not fit, large not large, and then it builds a curve for each question separately, and then they average the AUC score. So now question 2. What relevant baselines can be used for comparison? So we have one baseline, logistic regression, using only the explicit features, right? So numeric and categorical columns that's already present in the data set. So no embeddings for this. And then the output, again, small or fit or large, right? So that's the baseline. And question 3, how will you assess the validity of your model's predictions? So my models are reproducible. I used 42 as the seed, and there was no data loss. I basically imputed for all the missing values, and then I tuned the hyperparameters with grid search, and then I used multiple models, and the results from all these models were quite consistent. And so that supports the validity of my model's predictions, I hope. Now, section 2, EDA data collection, pre-processing, discussion. Question 1, context. Where does your data set come from? So it comes from the website Run the Runway, and according to the paper from dataset provider, Run the Runway is a unique platform that allows women to rent clothes for various occasions. Question 2, what is it for? How was it collected, etc.? So this was a public data set you can obtain from the website. It was obtained by Misra et al. For research purposes for the paper. Now, question 2, discussion. Report how you processed the data and how it was already processed. So the data was not processed. We had to pre-process it on our own. So here are the steps, my steps. So most columns were string or object type. And so basically I parsed some of those columns and converted them to numeric columns. For example, weight, I removed the pounds. Height, I changed the foot plus inch format to inch only. And then for bust size, I parsed that to 2 columns, band size plus cup size, and then I converted the cup sizes to numbers based on the rankings. So AA cup is 0, A cup is 1, etc. And then after that, I imputed the missing values. So for continuous numeric columns, I use median, right? Specifically for age, I replace both the missing and 0 values with the median because age 0 doesn't make sense, right? And then for ordinal numeric columns like cup sizes, I imputed using the mode. Categorical columns, we just added a new category missing. And then we did one-hot encoding for the categorical columns. Then we dropped columns that we shouldn't be using. For example, columns that will leak fit info. For example, rating, review summary, review text. So these columns are provided by the users after they know if the item fits or not. So that's gonna basically tell you whether the item fits or not. So we shouldn't be using those. And then we split the data sets into training and validation test sets. So 80% was training, 10% validation, 10% test, same as the data set provider. And then we scaled the numeric features using a standard scaler. So that means the mean is going to be 0, standard deviation is going to be 1. So basically we're going to apply the scalar on the training set and then apply that scalar on the validation test sets. Right, that's the best practices. And then we're gonna be looking at the code, right? Support your analysis with tables, plot statistics, etc. So EDA, we're only gonna be analyzing columns that we will use. So first, let's look at the class imbalance. Okay, dataset, class imbalance. Here you go. So 73.8% is fit, and then small and large about 13%. That's a big imbalance. And then there was no user IDs or item IDs missing, but then the user transactions are sparse, meaning that Wait, let's take a look at the plot first. Not the plot, but some data. If you look at here, user ID, the mean number of transactions is 1.8. So the average user has like 1 or 2 transactions, which is not a lot. Item ID though, so the mean item has about 33 transactions. So item IDs aren't sparse. The items aren't sparse. User transactions are kind of sparse. That means using only the user item embeddings as input to the recommenders may not work very well due to the sparsity of user transaction. And so we input both the explicit features and the embeddings, right? So we kind of do this hybrid approach to deal with this sparsity problem. And no item info are missing. So size and category. So size of the item, category of the item, none of that is missing. You can see that here. Size is none of them is missing, right? It's the same as the total rows. Category as well, same as the total. But then when it comes to user info columns, all user info columns have missing values. So age, weight, height, bust size, body type, renter for. We're going to be looking at all of that. So this is age. So you see here there's some missing values and there's some 0 values. And then this is the weight and height. A lot of missing weights, a little bit of missing height. Band size and cup size. As I said, I separated the bust size into band size and cup size. You can see here there's some missing band sizes and missing cup sizes. These two should be the same in terms of quantity because they come from the same column. And then body type, some missing values. Event category, so why did you rent this? There's a little bit of missing, I think 10 or something. So that's all the plots I have for EDA. And now section 3 modeling. Question 1 context. How do you formulate your task as an ML problem? What are the inputs, outputs? What is being optimized? What models are appropriate for the task? So the ML problem input, we have explicit input, explicit features. So that's the user features and item features we talked about. Input features, basically user embeddings and item embeddings, right? The latent factors. Output, either small or large or fit. Optimization objective, right? What is being optimized? We are optimizing the weighted cross entropy loss. So not regular cross entropy, weighted to counter the class imbalance we talked about. And then what models am I gonna use? First, logistic regression using only explicit input, and then logistic regression using both explicit and implicit input. And then we're also going to be using neural network plus the explicit and implicit inputs. And now discuss the advantages and disadvantages of different modeling approaches. So logistic regression advantage, obviously that's less complex and more efficient and also more interpretable, and it's easier to implement. Disadvantage, it's less powerful in terms of finding complex interactions on its own. Right, so you basically have to tell it the hidden interactions, otherwise, it's not going to find it on their own. So we do this by basically creating new features via feature engineering, right? U minus V, U times V, we talked about this. And then MLP, multi-layer perceptron advantage is more powerful in that it can find complex interaction on its own. So it'll know U minus V and U times V without us telling it explicitly. Disadvantage of that, usually less interpretable, and it can overfit sometimes. Okay, so let's keep going for now. We'll look at the code for section 3 and 4 together at the end. So section 4, evaluation. Question 1, context. How should your task be evaluated? Can you justify why your particular metrics are more appropriate than others? So we are dealing with the imbalanced multi-class classification task, and we should use ROC-AUC, more specifically 1 versus rest ROC-AUC as the evaluation metrics. Justification for that, we shouldn't use accuracy. A classifier that predicts fit for all inputs would have a 73.8% accuracy, so that's not good. And then what are we optimizing? We are optimizing the weighted cross entropy loss, and the justification for that, for using weighted cross entropy loss, is that standard cross entropy loss treats all the errors equally, whereas weighted cross entropy loss, they'll penalize errors on minority classes more, which is what we want, because those minority classes actually matters a lot. And then question 2, discussion. What are some baselines for your task? How do you demonstrate that your method is better than these methods? So we implemented in total 6 models. The baseline is the logistic regression on explicit features. The result was 0.6211. And then we had 2 more logistic regression models. One is trained on explicit features plus U minus V. So that's 0.7126. And the best embedding dimension for that was 1. And then another LR on U times V. This time the result was 0.6776. Best K was still 1. And we had 3 MLP models. 2 of them we explicitly told it to consider U minus V and U times V. So we had 2 middle layers. The result was 0.6877 and 6866. Pretty similar. But then for U minus V, the best dimension was 20 for U times V, the best dimension was 1. And then we had one final MLP model, but we didn't tell it anything. We just gave it the embeddings, and we're going to see if it can figure something out on its own. So again, we had 2 middle layers. The result was slightly better, 0.7082. The best dimension was 1. So here are my interpretation of the results. So U minus V is physical. U times V represents, indicates preferences, right? As we talked about. So when we look at the LR models, U minus V had a higher AUC, meaning that at least for LR, U minus V was better, right? And then MLP, looking at these 2 models, they had a similar score. However, U times V, it did worse as K increased, whereas U minus V did better as the embedding dimensions increased. My interpretation for this is that when you add more latent variables that represent physical properties, it worked better. But then adding more latent variables that represent preferences, it just added more noise and interactions that didn't make much sense, which is why increased dimensions on U minus V was better. And now comparing the strict MLP models versus the general MLP models, we can see that the general did better, right? It scored better, which is kind of expected because MLP are designed to figure out complex interactions on its own. But one thing to note that is that the general model did worse as the K increased, which is kind of surprising. But my interpretation for that is, the equation that really mattered was just U minus V. And adding more dimensions made it harder for the model to find that simple interaction that mattered the most. Which kind of explains why the general model did worse as K increased. But that's just my interpretation. Now, looking at logistic regression versus MLP. So you can see that for U minus V, right? For U minus V, LR did better. U minus V, LR did better, right? My interpretation for this is that so U minus V is the simple linear interactions that matters the most. And so there's no complex interaction needed. And in this scenario, LR does do better than MLP because MLP is designed to discover, complex non-linear interactions, right? And then looking at U times V, the MLP did better, slightly better. So, right, this versus this. And why is that? U times V isn't the right interaction for the task, is my interpretation. The MLP compensates for this by learning nonlinear correction functions, which is why the MLP did better for U times V. And now let's look at the code. So here we have the baseline model. As you can see, we use logistic regression on the explicit dataset only. And we had the score 0.6211, as we mentioned. And here we're setting up PyTorch because that's what we are going to be using for the other models. And here we have the logistic regression using the difference model. So here you can see we have BU minus BI, U minus V, and here is the LR for the U times V. As you can see, we are giving it the explicit features, user bias, item bias, and then U times V. I'm not sure if we talked about why we are doing subtraction for the biases for U minus V. But the reason is because if we treat the embeddings as physical metrics, the bias is going to cancel out. So if a user always complains about something being big and the item is always being complained that it's too big, it's going to cancel out, right? Because it's going to fit for the item is going to fit for the user. But then if we treat the embeddings as preferences, the U and an I, they don't cancel out. So we feed the biases separately. And then we do hyperparameter tuning. And we have the training loop 10 as the epoch. And then evaluation on the test set. Here are the results. So for the difference model, the result was 0.7126. The product model result was 0.6776. And then you can see here the best dimension was 1 for both of them, as we mentioned. And here are the MLP models. So here, the first one, we tell it explicitly to think about U minus V. For the second one, we tell it explicitly to think about U times V. For the final and general one, we don't tell it anything. We just give it the explicit feature and the embeddings to see if it can think of something on its own. Again, hyperparameter tuning, and then evaluating on the test set. And as you can see here, for the difference model and the product model, it's pretty similar. But then the dimensions are completely different. You can see as the dimension increased here, it generally got better. But here, as the dimension increased, it became worse and worse. And then finally for the general one, right, it scored a bit better. And again here, as the dimension increased, the model performed worse. We also talked about this. So that's all my code. Thank you for listening.